Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on complex analysis, power series lecture number 5, in which I will give the technique to examine the behavior of power series at different points. Now we solve a problem. Problem is, if R1 and R2 are radii of convergence of the power series sigma an z to the power n and sigma bn z to the power n respectively, then so that the radius of convergence of the power series sigma an bn z to the power n is R1 multiply R2. Now we solve this. Let R1 be the radius of convergence of the power series sigma an z to the power n. Therefore 1 by R1 equal to limit n tends to infinity modulus of an to the power 1 by n. This is number 1. Again, let R2 be the radius of convergence of the power series sigma bn z to the power n. Therefore 1 by R2 equal to limit n tends to infinity modulus of bn to the power 1 by n. This is number 2. Let R be the radius of convergence of the power series sigma an bn z to the power n. Therefore 1 by R equal to limit n tends to infinity modulus of an bn whole to the power 1 by n. This is equal to limit n tends to infinity modulus of an to the power 1 by n multiply modulus of bn to the power 1 by n equal to limit n tends to infinity modulus of an to the power 1 by n multiply limit n tends to infinity modulus of bn to the power 1 by n. Using 1 and 2 we get this is 1 by R1 and this is 1 by R2. Using 1 and 2 implies that R equal to R1 multiply R2. Proved. Now we solve the next problem. Problem is, find the radius of convergence of the power series fz equal to sigma 0 to infinity z to the power n by 2 to the power n plus 1, and prove that under bracket 2 minus z fz tends to 2 as z tends to 2. Since an equal to 1 by 2 to the power n plus 1 and n plus 1 equal to 1 by 2 to the power n plus 1 plus 1. Let R be the radius of convergence of the given power series. Therefore 1 by r equal to limit n tends to infinity modulus of a n plus 1 by a n equal to limit n tends to infinity modulus of 1 by 2 to the power n plus 1 by 1 by 2 to the power n plus 1 implies that 1 by r equal to limit n tends to infinity 2 to the power n plus 1 by 2 to the power n plus 1 modulus this equal to limit n tends to infinity 2 to the power n plus 1 by 2 to the power n multiply 2 plus 1 equal to limit n tends to infinity 2 to the power n plus 1 by 2 to the power n by 2 to the power n multiply 2 plus 1 by 2 to the power n this equal to limit n tends to infinity modulus 1 plus 1 by 2 to the power n by 2 plus 1 by 2 to the power n. Here n be non-negative number, so no need to use this modulus, only we may write a bracket, simple bracket. Using limit n tends to infinity, we get 1 plus 0 by 2 plus 0 equal to 1 by 2, implies that r equal to 2, that is radius of convergence equal to 2. Therefore, the given series converges at the points inside the circle of radius 2 and center z equal to 0. Here this is a circle whose center is z equal to 0 and radius be 2. The series is convergent at the points inside the circle. Since given that fz equal to sigma n equal to 0 to infinity z to the power n by 2 to the power n plus 1, and this is less than sigma 0 to infinity z to the power n by 2 to the power n. This is equal to, if n equal to 0, then 1 plus n equal to 1, then z by 2 plus n equal to 2, then z square by 2 square dot 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 dot. This series is in GP with common ratio z by 2. So this will be equal to 1 by 1 minus z by 2, since the series is in GP with common ratio z by 2. This equal to 2 by 2 minus z implies that 2 minus z fz tends to 2 as z tends to 2. Proved. Now we solve the next problem. Next problem is examine the behavior of power series sigma minus 1 to the power n z to the power n by n on the circle of convergence. Now we solve this. Here a n equal to minus 1 to the power n by n. Let r be the radius of convergence. Therefore 1 by r equal to limit n tends to infinity modulus of a n to the power 1 by n, and this is equal to limit n tends to infinity modulus of minus 1 to the power n by n to the power 1 by n is equal to limit n tends to infinity modulus of minus 1 to the power n by n to the power 1 by n, and this to the power 1 by n. This is equal to limit n tends to infinity minus 1 modulus n to the power 1 by n. This is equal to limit n tends to infinity 1 by n to the power 1 by n. Let this is number 1. Let x equal to n to the power 1 by n implies that log x equal to log n to the power 1 by n equal to 1 by n log n, taking limit n tends to infinity log x equal to limit n tends to infinity log n by n using L'Hospital's rule. Derivative of log n equal to 1 by n and derivative of n equal to 1 using L'Hospital's rule. This is equal to limit n tends to infinity 1 by n. If n is infinitive, then this equal to 0 implies that here log base x equal to 0 implies that x equal to e to the power 0 equal to 1 implies that x is here limit n tends to infinity, here limit n tends to infinity, limit n tends to infinity, x means n to the power 1 by n equal to 1. This is number 2. Using 2 in 1, we get 1 by r equal to limit n tends to infinity 1 by n to the power 1 by n. Here limit n tends to infinity, n to the power 1 by n is 1. So this is will be 1 implies that r equal to 1. Therefore, radius of convergence equal to 1. Therefore, the series is convergent at the points inside the circle whose radius is 1 and center be the origin z equal to 0. That is, if we take this circle whose center is 0, radius is 1, then series is convergent at the point inside the circles. Now we think about the convergency of the power series on the circles, that is the points on the circumference of the circle. Since the power series is sigma minus 1 to the power n by n z to the power n. Now this is the x-axis and here z equal to minus 1, here z equal to plus 1. Number 1, at z equal to minus 1, the power series will be sigma minus 1 to the power n by n minus 1 to the power n. This equal to sigma minus 1 to the power 2n by n. This is equal to sigma minus 1 to the power 2n is 1 by n, which is a divergent series. Therefore, at the point z equal to minus 1, the series diverges. Let we examine the behavior of series at other points on the circle. Number 2. Let un equal to minus 1 to the power n z to the power n and Vn equal to 1 by n. Let Sn equal to sigma un 1 to n. So this is equal to minus z plus z square minus zq plus dot plus minus 1 to the power n z to the power n modulus. This is in GP. First term is minus z multiply 1 minus z to the power n by, here common ratio is minus z, 1 minus z. Since the series is GP with common ratio minus z, this is equal to modulus. If we multiply this, minus z minus plus minus z to the power n plus 1 by 1 plus z. here z not equal to -1 we take. Implies that Sn less than equal to modulus of minus z plus modulus of minus z to the power n plus 1. Here modulus of 1 plus z. Modulus of minus z on the circle, this is 1 plus here also modulus of minus z on the circle 1 to the power n plus 1 by 1 plus z modulus. Since on the circle modulus of minus z equal to modulus of z equal to 1 implies that Sn less than equal to 2 by modulus of 1 plus z. Therefore, Sn is bounded. That is partial sum of sigma given is bounded. Now, modulus of Vn minus Vn plus 1 equal to Vn is 1 by n minus 1 by n plus 1. This is equal to n into n plus 1. Here n plus 1 minus n, and this is equal to 1 by n into n plus 1 implies that sigma modulus of Vn minus Vn plus 1 equal to sigma 1 by n into n plus 1. Here no need to use modulus here. Here we may use the modulus, here no need because n is non-negative number and this is less than sigma 1 by n square, which is a convergent series. This is number 1, this is number 2. Now, limit n tends to infinity, Vn equal to limit n tends to infinity 1 by n equal to 0. This is number 3. Therefore, from 1, 2 and 3 we get sigma un Vn is a convergent series at the points on the circle of radius 1, center z equal to 0, except the point z equal to minus 1. That is sigma minus 1 to the power n by n z to the power n is convergent at the points on the circle of radius 1, center z equal to 0 except the point z equal to -1. So our problem is solved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.